Welcome back to our lecture series on advanced hydraulics. We are now starting today the module 4 on hydraulic jumps. If you recall our earlier lectures and all, we had covered 3 modules. First module was on open channel flows. We discussed there on the types of open channel flows, what is meant by the velocity distribution, what is meant by critical flow. In the second module, we discussed on uniform flow. We have discussed on the Manning's equations, Chassis equations. Also, we have discussed on the coefficients, roughness coefficients, how to design economical sections, etc. Subsequently, in the third module, we discussed on the varied flows like gradually varied flow, spatially varied flow. We had derived the dynamic equations to understand the gradually varied flow or to compute the gradually varied flow profiles. What are the classifications of gradually varied flow, that also we had studied. Today, we will start on the fourth module, that is on the hydraulic jumps. So, the first question you would like to pose is, what is meant by hydraulic jump? A hydraulic jump is a type of rapidly varying flow. So, as stated earlier, till the last module we studied on gradually varied flow, as well as the spatially varied flow also. The flow profiles were occurring, the change in the flow profiles were gradual. So, here the rapidly varying hydraulic jump is the change in the water profile that occurs in a rapid form. You see here, this is the water surface profile, maybe it is a supercritical flow and here it is a subcritical flow. All of a sudden, the depth of the water changes in a short reach. So, all of a sudden it jumps to a higher level. So, this is a hydraulic jump. You can see such phenomenon in lot many places in the nature, as well as in the canals, in the engineered flows, in dams, structures and all. You will see in many locations hydraulic jump. So, as we suggested earlier in the last module and all, we had discussed on gradually varied flow. In the last class, we discussed on the features of spatially varied flow, if you recall them. Features of spatially varied flow. We did an example problem on the spatially varied flow for a rectangular channel and all. So, in all those situations, wherever possible, we had taken almost a parallel flow approximation. Even the gradually varied flow or even the uniform flow distribution and all, we had taken the parallel flow assumption. Here, we will just go through what is meant by rapidly varied flow. So, rapidly varied flow, which have a rapid change in the flow profile, those flows are called rapidly varying flow. What is rapidly varied flow? Again, I am posing the question in front of you, if any guess and all, because we have already studied the gradually varied flow. So, can you come up with an idea on what is meant by rapidly varied flow? Wherever there are pronounced curvature, in the flow profiles or streamlines, it causes rapidly varied flow. Say if there is a channel bed like this, the streamlines up to the water surface, say if you try to draw it, say maybe in this location, you can see, and let this be the water surface. The streamlines, if you draw it, you can see the curvature of the streamline. It is rapidly varying. Within a short reach itself, it is rapidly varying, and the streamline curvatures two adjacent streamlines are not having same curvature. So, this causes a rapidly varied flow situation. You may encounter such type of flow in various locations. So, what rapidly varied flow, usually it is defined as the rapid or pronounced variation in curvature of the flow profiles, both in as well as the water surface as well as the streamlines. If there are pronounced curvature in those lines, those type of flows are called rapidly varied flow. You may see that in some places the flow profiles gets broken. The water surface it may get broken. That is also a type of rapidly varied flow, and we will see what is that type of rapidly varied flow called. Where are the rapidly varied flows seen? Where do you see rapidly varied flow? Say, here I have just drawn a rectangular channel, maybe a sloping channel, and there is a free overfall of water. Now, if this free overfall of water, if you closely look into that, okay, we do not know the depth of the flow, what is where it is merging and all, but this free overfall, here the flow patterns, it means it is rapidly changing from at this location, it is rapidly changing. The curvatures of the flow, it is changing. It is an example of rapidly varied flow. I can just give in a more detailed way. If you look into the second module of the course, in the second module, we had mostly dealt with uniform flow approximations. You had dealt with the uniform flow approximations in open channels. So, there the flow was considered parallel. Also, we suggested that streamlines are parallel to the bed slope. Like this also we had suggested in the uniform flow assumptions, but seldom in the nature you may encounter uniform flow. Therefore, uniform flow may be only in a very engineered situation. Suppose a canal is being designed and a canal is designed in such a way that you have to carry so and so amount of discharge regularly without any fluctuation, and after a certain time it becomes a uniform flow in that canal and all. So, such situations are very rare. In nature, river cannot have uniform flow in every location, because the boundaries of the river, they are varying. The boundaries are not, most of the rivers may not have a concrete, means a solid boundary, that is solid means non-erodible boundaries and all. So, you may encounter varied type of flows. So, in rivers or even in natural streams, channels and all, you cannot give a uniform flow approximation at all times. Maybe at certain extent, certain duration of the time or certain portion, you may be able to approximate uniform flow assumptions and all, but that is not true in all the senses. Therefore, the second module, in whichever we have studied uniform flow approximations, we may have to modify them for the natural channels. In the third module, again in the third module, we had given gradually varied flow approximations, or even in the spatially varied flow, the flow profiles were changing gradually. Also we suggested that the curvature of streamlines the curvatures of streamlines, they were changing gradually. Therefore, in such situations you were able to incorporate the parallel flow assumptions. So, you were able to incorporate the parallel flow assumption. What is the parallel flow doing? Parallel flow means you consider hydrostatic pressure conditions. You consider hydrostatic pressure conditions, but in rapidly varied flow, you do not have parallel flow. Therefore, no hydrostatic pressure. So, you may have to use different theory there. Actually, our question was, where do you often see rapidly varied flow? So, now to come into that, you will see rapidly varied flow, maybe first flow over a weir. If I want to just draw that, say a channel is there or a stream, whatever be. If you are constructing a weir, maybe rectangular, triangular, whatever shape you can assume them. A weir is being constructed to block the flow. Now, what happens? Whatever flow overflow means that occurs by overflowing or flowing over through this weir and all. So, it falls like this, right. So, if the channel was already having a uniform flow earlier, now it may just dip like this. Okay. So, here the change in profile is not gradual. In this stretch, you can suggest that this is a rapidly varied flow profile. Water surface, it is dipping sudden. So, flow over a weir has means in flow, wherever flow occurs over a weir, you will be encountering rapidly varied flow. Similarly, and another example I can quote here is flow under a sluice gate. So, these examples are clearly described in Professor Rajesh Srivasta's book on open channel hydraulics. You can refer them also for more details and all. I will just briefly explain here. Say if there is a sluice gate that is blocking the flow, maybe in the uniform channel flow channel and all. So, you know that there will be a gradually varied flow profile in the upstream of the sluice gate, that is quite understandable. Now, due to the narrow passage in the bottom, the flow here gushes up and flow profile changes like this, means. So, this entire stretch, it is having a rapidly, in this small stretch itself, the flow profile or the curvature of the flow, it is changing rapidly. So, it is having a rapidly varied flow profile. Another example we can see is wherever a canal fall or canal drop is there, as we have seen here in this particular figure. This is a rectangular canal or channel, there is a canal drop or a canal fall. Now, this also gives you a, say I can draw the cross sectional form now like this, say if there is a canal and it is dropping like this, whatever flow was there now. So, in this entire stretch it is having rapidly varied flow. This is also a rapidly varied flow profile like this along the drop. So, such phenomenons you can see in various phenomenons you can see in rapidly varied flow. A most important of the rapidly varied flow profile is the hydraulic jumps. There is a canal, here some low depth flow is there, here a large depth flow is there. The flow within a short reach, it jumps to the higher elevation, from lower elevation to higher elevation, it jumps all of a sudden. It is caused by various reasons. We have not come into the scientific study, that will be going in our later classes and all. So, but in that short reach, the elevation of the water jumps from a lower elevation to a higher elevation. So, this causes this is a rapidly varied flow phenomenon, and it is the most common of the all of the most common phenomenon you will witness in rapidly varied flow. Even in this entire module we have named it as a hydraulic jump, although it can be called, this module could have been renamed, or it could have been more in a more general way called as rapidly varied flow. But because we will be studying in more detail on the hydraulic jumps and its aspects for the open channel engineer design of the canals and all, we have given the name or name of the module as hydraulic jumps. What are the rapidly varied flow characteristics? How can I suggest that a flow is rapidly varied flow? What are its general characteristics? So, as we mentioned earlier, rapidly varied flow will be having pronounced curvature in flow profiles, both water surface as well as streamline. So, these quantities will be having pronounced curvatures. So, based on that the flow is considered as rapidly varied flow. So, as the curvature is significant, you cannot take hydrostatic pressure distribution in flow. You cannot take hydrostatic pressure distribution in flow. So, then this takes place, we also suggest that rapidly varied flow takes place in a short reach, unlike the gradually varied flow. If you recall the gradually varied flow, we suggested that the gradually varied flow phenomenon occurs in a large reach, maybe up to 2 kilometers, 3 kilometers and all we had suggested. We had done some examples on that. But rapidly varied flow, it occurs within a short reach, within a say 1 meter, 2 meter, or within those things it occurs. So, what is the significance of this short reach? Due to the rapid, due to this thing, say I can suggest that one of the characteristics, due to short reach, your control volume for analyzing rapidly varied flow, that will also be having a small length. Due to short reach, you can neglect frictional forces and gravitational forces. Please note that you can neglect frictional forces and gravitational forces in the direction of flow. We are not talking about in the vertical direction. In the direction of flow, you can neglect them. In the direction of fluid flow, the vertical components still exist and we are not neglecting them. Again, one of the characteristic you have is that there will be rapid change in a cross sectional area, cross sectional area of the channel or stream, whatever be. So, due to this rapid change in the cross sectional area, your velocity distribution coefficients, like energy correction factor alpha, momentum correction factor beta and all, they will be much greater than 1. So, you cannot neglect them in the analysis, you may have to use them always. In most of our earlier studies, we had neglected or we have approximated these quantities as 1. So, you cannot do it in rapidly varied flow. Some of the rapidly varied flow means or the rapidly varied flow phenomenon, it may have, or I can rewrite it here, rapidly varied flow may have continuous water surface profiles or discontinuous water surface profiles. So, continuous as we have seen in say, we have suggested that flow over a weir, flow over a spillway, whatever. Now, you see here, the water surface here in these regions and all, say this is spillway or we yeah. So, here the profile is rapidly varying within a short reach. Still due to the rapid change in the profile is not, water surface is not getting discontinuous, it is still continuous. However, in jumps, if you recall them, you have disjointed water surface profiles here. So, you can in the rapidly varied flow, therefore, you can have both continuous water surface profiles or discontinuous water surface profiles. A classic example of discontinuous water surface profile rapidly varied flow is hydraulic jump. How to approach rapidly varied flow? How do you approach in general the rapidly varied flow or for analyzing the rapidly varied flow and all? So, we suggested that for both for uniform flow and gradually varied flow, you were taking hydrostatic pressure distribution. That cannot be taken here for the rapidly varied flow. So, the theory which suggested parallel flow or hydrostatic pressure distribution, this was formulated long back by Bresci as stated in Venti Chow's book 1959 book. So, this is called Bresci's theory. the concept of parallel flow or taking hydrostatic pressure distribution for fluid flow. So, that Bressy's theory is not valid for rapidly varying flow. So, what we have to do is that we have to check or verify whether we can mathematically analyze fluid flow in rapidly varying conditions. So, is it possible? So, according to the fundamental principles, if you take the control volume approach and all, it should be possible, but how far? What are the assumptions required? What are the quantities required, or what all simplifications you may need to do to understand or to analyze the rapidly varied flow, that we need to go through. So, the scientist had worked on that by say you know that Navier-Stokes equation, that has been derived using the momentum approach and all, it is the fundamental equation for fluid flow. So, by incorporating proper assumptions, you can suggest Navier-Stokes equations for fluid flow in open channels also. In addition to that, if you incorporate inviscid regions of fluid flow as well as potential flow regions, if you incorporate these two assumptions in the Navier-Stokes equation, then you will be able to get a mathematical form for rapidly varying flow having continuous profiles. Please note that having continuous profiles, you will be able to describe mathematically based on the assumption that is the region is having inviscid flow, then it is also having potential flows. On those assumptions, you will be able to mathematically describe rapidly varied flow for a continuous profile. The solutions for such type of governing equations, the solutions of such mathematical equation it can be obtained by understanding the curvature of water surface. By understanding the curvature of water surface, you can analyze such mathematical equations. So, from earlier days several scientists long back, maybe some few 60 years before itself and all, they have started analyzing them. For example, scientist Boussinesq, this is given in Ventichow's book. He developed a theory, that is, he assumed that linear increase of curvature of streamlines from channel bed channel bed to the curved flow surface. So, what is the meaning here? Say if you have a channel bed like this, from this channel bed he suggested linear increase in curvature. So, maybe like this, like this, like this. So, there could be a linear increase as we go from the up to the curved surface, whatever be. So, there will be a linear increase. The curvature of the flow profile, it is increasing linearly with respect to the depth. That was a simple assumption incorporated by Boysinus, and he then started he analyzed the fluid flow for rapidly varying conditions. So, they will use the momentum equations and all to solve such fluid flow problem. Another theory was suggested by Favre. This is also described in Penty Chow's book. So, it assumed exponential variation in curvature with the distance from channel bed. So, as you move away from the channel bed, the curvature of the streamline increases exponentially. So, you can just substitute and see how the curve looks. So, maybe it could be like this, it can be like this. So, it is up to you to decide within a particular stretch, how the curvature varies. So, these are all old theories. Now, in this modern age, you are able to analyze using computers and computational methods, or even graphical methods. So, there are advanced computers that use good graphical methods, or there are advanced instruments that are able to use maps or proper graphs and all. They will be able to interpret the flow profiles and all. So, graphical methods are also used, computers are also used. So, in this age you can still you will be able to analyze the rapidly varied flow in a much better way. Still, although these things are there, as you mentioned, this is for the continuous flow profile. A general solution for the rapidly varied flow for all aspects, it is still not available. Scientists have since then worked in such a way that they consider the various phenomena of rapidly varied flow as isolated cases, means they consider rapidly varied flow having different isolated cases. Each of them are having their own solutions, maybe empirical, maybe mathematical, whatever be. So, they will be analyzing it in a, for example, they consider hydraulic jump entirely as a different phenomenon. Flow over a spillway, they consider as a different phenomenon. So, they may be having a different approach for each of the solution. You cannot have a general solution that will solve both the flow over a spillway as well as hydraulic jump as well as flow under a sluice gate and all. So, you have to analyze it in an independent way. Now, for analyzing rapidly varied flow, we suggested that the curvature is pronounced in rapidly varied flow. For example, in the hydraulic jump, within a short reach the elevation of water rises. So, if you use your standard continuum approach, that is with control volume and all, you have to select the continuum or control volume in such a way that it is incorporating the entire details of the rapidly varied flow. So, here now we are taking the control volume as shown in the box here for the hydraulic jump. Say for the sluice gate, your control volume should be such that it is incorporating the details, because the pressure, the reason is that the control volume should be appropriate. It is due to the sense that you are not taking hydrostatic pressure distribution. So, if you are not taking the hydrostatic pressure distribution, then whatever flow is there, whatever pressure distribution is available, you may have to take into that consideration. For that, you have to evaluate pressure at those locations which are not hydrostatic in nature. Those phenomenon, if you in this particular for the sluice gate, at this entrance of the sluice gate, you know, here you can take the pressure as hydrostatic, but you will not be able to take the situation everywhere in that situation downstream, everywhere in the downstream you will not be able to take it as hydrostatic. So, at the entrance it was possible. So, if you incorporate your control volume starting from that, then at the outlet of the control volume it is easier to evaluate pressure. So, we will start this module on this first with the hydraulic jumps itself. Then later on we will briefly cover the other types of rapidly varied flow. So, hydraulic jump. The definition of a hydraulic jump is when a supercritical flow in an open channel meets a subcritical flow it causes a sudden jump in the flow depth. This is hydraulic jump. Fine. So, you know that in supercritical flow, you have low depth as well as high velocity, right. So, that means low depth high velocity flow, if it meets high depth low velocity flow, then there is a sudden jump in the elevation, that is given as hydraulic jump. You can similarly write for subcritical, it will be having large depth, low velocity. Fine. So, some of the examples of hydraulic jump, as we have we are taking it from Srivastav's open channel book that was published in 2009. So, those examples we am just again quoting it here. Some of the classic examples where we can see hydraulic jump. See, if a steep slope channel meets a mild slope channel, what happens? A steep slope channel means a mild slope channel. So, here the depth of flow, it is low because it is a supercritical flow, and here the depth of flow, it is considered as subcritical, Now, there is a significant difference in the elevation. So, here there occurs a sudden jump up to the means from the supercritical depth to the subcritical depth of the mild slope channel. So, this is a jump, this is a hydraulic jump. So, here we have a steep slope channel and a mild slope channel. So, this causes sudden channel. So, the supercritical depth in the first channel changes to subcritical depth in the second channel. Another example we can see for hydraulic jump. Say if you have a sluice gate, you know that flow under a sluice gate is supercritical. Now, if this supercritical flow meets a uniform flow or subcritical flow in the downstream, it causes hydraulic jump. So, I can just show it in the diagram. There is a sluice gate, flow occurs. We consider that the downstream there is a uniform flow. Now, the flow here it becomes a rapidly varied flow, means it is a supercritical flow. Now, it gushes at a high velocity, this becomes it is a supercritical flow. Then after that it all of a sudden it jumps to the subcritical flow or uniform flow conditions and all. If this uniform flow it is maintained as it is in the downstream, then such type of events occur, such hydraulic jump occur. So, this uniform flow in the downstream can be maintained by various methods and all. So, those things we are not studying right now here, we are studying that wherever hydraulic jump occurs, that is those locations we have specified now. Another example you can see is that if there is a spillway, and the downstream depth of water is having a certain depth, water flows over a spillway at a high speed and at a low depth along the spillway, and it reaches here. See the depth here and all, here it is very small, but here in the downstream however, we are having a larger depth. So, this change in depth causes a hydraulic jump. See, this is the spillway, water is flowing over the spillway like this at a high velocity, and there is a low velocity depth here. This low velocity can be maintained by various basins and all, you can incorporate them. So, once this low depth is available, low velocity depth is available here, this causes a hydraulic jump. So, we can say low velocity water here, and this is high velocity water. So, this also causes a hydraulic jump. So, properties associated with hydraulic jump. So, hydraulic jump, if you look it practically or if you look it in a simple way in the layman's form itself, you know that in the upstream it is the water is coming with a high velocity, in the downstream water is going with a low velocity. That is the general form of hydraulic jump. So, what it is actually doing? when water is coming with a high velocity, it is having a high kinetic energy and all, and when it is going out with a low velocity, that is some energy is getting dissipated. So, this energy dissipation of energy, it can be beneficial for the fluid flow in the channels and all. So, most of the time hydraulic jump is used as a energy dissipation unit also, but that we will come into later also. Hydraulic jump, it is used as energy dissipation unit. Hydraulic jump is also used for mixing chemicals. Suppose if you mix chemicals in the a very high velocity, water is coming here, if you mix chemicals here, it gets mixed entirely thoroughly in the water. For mixing chemicals, you can use hydraulic jumps, or for aerating water, or to increase dissolved oxygen. For that also you use hydraulic jump. So, hydraulic jumps, they are usually means some of the things, aspects or parameters you have to you require for analyzing hydraulic jump. Some of the parameters required for hydraulic jump, we can suggest, say, energy loss as a parameter. You can also associate say the energy at this location upstream and energy at this location, whatever change in energy is there, that energy loss. If you are designing a hydraulic jump based on energy loss, so then energy loss becomes a parameter. Flow depth, say if you are designing based on flow depth, you have a upstream flow depth, say y 1 here, and downstream flow depth y 2 here. Based on the flow depths, difference in flow depth, you can design the flow, you can design the hydraulic jump. Based on the length of the hydraulic jump, say from here to here, how much length is required, how much length you have suggested, that also becomes a parameter. Location of the jump, whether it is below a spillway, whether it is below a sluice gate, what will be location of spillway. So, these are some of the parameters that are essential for analyzing hydraulic jump. So, we will be using these parameters in our next class. We will be studying, you will be using the continuum approach, that is the control volume approach for studying the hydraulic jump, and these parameters will come into picture there also. So, that way we are concluding today's lecture. We can take a brief quiz now. So, the first question for the quiz is, briefly explain in 1 or 2 sentences what is meant by rapidly varied flow. That is, briefly explaining 1 or 2 sentences what is meant by rapidly varied flow. Your second question is, cite few examples of rapidly varied flow phenomenon. Cite few examples. The third question, what is hydraulic jump? Say whether the hydraulic jump has a continuous or discontinuous flow profile. So, the solutions for today's quiz. The first question we asked is, briefly explain in 1 or 2 sentences rapidly varied flow. So, I can easily suggest rapidly varied flow are nothing but where flow that is having variations in profile in a rapid stretch, in a rapid form. So, they have rapidly varied flow have pronounced curvature in streamlines, it occurs in a short stretch. That is why it is called rapidly varied flow. Like this you can answer them. Your next question asked was cite few examples of rapidly varied flow. So, we have, I will just give it in a figurative way again. Standard example is the hydraulic jump. This is an example of rapidly varied flow. Another example is canal fall or canal drop. We suggested that. So, this is having rapidly varied flow profile, this is having rapidly varied flow profile. We also suggested about the sluice gate. In the sluice gate, so under the sluice gate the flow profile rapidly changes. So, this stretch is also a rapidly varying flow profile. Okay. So, there are various examples, you can quote, you can write some other examples also if you are aware of them. Our third question, what is meant by hydraulic jump? Say whether the hydraulic jump has continuous or discontinuous flow profile. We can suggest that again. Hydraulic jump is defined as when a flow or when a supercritical flow meets a subcritical flow, it causes a sudden jump in elevation of water surface. This is called hydraulic jump. So, the second part of the question, whether hydraulic jump is continuous or discontinuous. Hydraulic jump, we suggested that hydraulic jump is having discontinuous flow profiles. So, hydraulic jump is having discontinuous flow profiles. So, that way we are given the solutions also for the today's quiz. Next class, as we mentioned earlier, we will be dealing with the theoretical aspects of the hydraulic jump, its benefit, how do you analyze the flow phenomenon there, all those things. Thank you.